Hello everybody, welcome back after the lunch. So I'm happy to invite our next speaker, Mr. Pete Davies, Senior VP Digital Engineering Solutions, Uniper. He'll be speaking on continuous safe operations as competence declines against the changing operations. And we're happy to inform that he's going to speak from London online. So we are request Mr. Pete to take it over and start his presentation. Pete, are you able to hear?
Yeah, hi Lena, I can hear you. So perfect, you can see me. How do I share my screen? Show my screen. Okay, can you see my screen?
Yeah, I can see your desktop. Yeah, right.
Perfect.
Yeah.
Good afternoon, everyone. So today I'm going to talk through how we at Uniper and some of our clients use digital solutions to deliver a safe operation, and some of our case studies come from the COVID era. So yesterday my colleague Pete Saddington spoke to some of you about who Uniper is, so I'll do a quick reminder of that. Then I'll use case studies to explain the benefits that we've achieved and some of our clients have achieved. And then I'll end with why is this possible and how can you achieve something similar. So we are Uniper, born in 2016, but in fact have a long pedigree history. Some of you will probably know Powergen International, as we used to own assets in India. But we then became E.ON, and in 2016 became Uniper. So long pedigree, but a new name, which has enabled us to build a new culture as well. We've got around 11,000 employees, predominantly based in mainland Europe and Russia. We have around 34 gigawatts of generating asset in mainland Europe and Russia. And all the other countries that are in a white color are where we provide services, solutions to clients. And this is coverage of what assets we have in our portfolio. So a large gas fire basis, a material coal basis, some large gas storage, energy storage. We trade around 4 times our asset base size for coal, gas, LNG and power. And a large amount of hydro and some around 2 gigawatts of wind in our traded portfolio. Myself, I work in the engineering section, engineering services and digital solutions area. And everything I talk through today really has been built on our pedigree of the challenges in Europe. So that's built on effectively a change in operation over the years. And to maybe put this into perspective, this is a typical day from October a couple of years ago. In the UK, we generally have an oversupply of renewables. So during COVID times, we're up to 50–60% renewables capacity being provided to meet the demand. But on this day, we've got a low demand basis. So therefore, our gas units are flexing and providing a start-stop cycling nature. We've also got some standby generators, so the wind does tail off quickly on some cases against the forecast. So the grid has to have some standby generators in place to manage that. And interestingly, this kind of brown line here is in fact one coal unit. So that was Ratcliffe coal unit, and it's there providing non-energy products. What I mean by that is it's not there for wholesale power. It's there for frequency response, megavars, voltage control, etc. And that's where a lot of the money in the UK is now, because of the required flexibility. Gas price sets the power prices in the UK. And when this was in place, there was 4 interconnectors. There's now 6. and they're all asynchronous, so they don't provide any inertia, which means that in the UK and in mainland Europe, we've had to change how our assets operate to take advantage of those opportunities in the market. To maybe make this a bit realer, this is the story of Ratcliffe Power Station, where I'm currently sitting today. This is time along the bottom, and this is the average number of starts per unit per annum. It's a 4-unit, 500 megawatt hard coal subcritical coal-fired station. You can see it was designed for base load between 3 and 10 starts per annum, and during the 1980s there was a coal shortage, so units had to come off and they had to do multiple starts. Then during the 1990s we had the dash for gas, so lots of gas-fired power stations were built in the UK, and that changed the market dynamic, and they became first in the merit order, which is similar to the US. And then in the 2000s we had renewables penetration. So the renewables penetration caused starting and stopping, but it caused increased cycling, lower minimum loads, etc. So what you can see here is we've taken a traditional asset designed for base load and taken it through 2 other modes of operation, so starting, stopping, and then cycling. And this is real, it was around here, the early 2000s, where the UK started to get around 10 to 12% renewables penetration. So once you're up at those 10, 12%, you will need your assets to start flexing depending on certain grid constraints. And to be able to do that, we've relied very heavily on digital solutions, even before it was called digital. So using the digital solutions, it allows us to balance our carbon intensity, our costs, and the consequence of not supplying energy to the community. And we're able to do that because of our background as an owner and an operator. The building where I work is from the research centre of the CEGB, and as a result of that, we've been able to maintain independence from OEMs and not being held mercy to equipment suppliers. And we've always had software capabilities in our organisation. To make that a bit realer, so 30 years ago, we built our own thermodynamic software. It's a bit more than 30 years ago now, because at the time there wasn't the tools on the market that were fit for purpose for us to achieve what we needed, particularly around radiant heat and the cyclical nature of heat exchange. Then around 25 years ago, we did online vibration monitoring. So the main shaft line, pumps, major equipment. 20 years ago, we did complex market modeling. So with the liberalization of markets in Europe in particular, how to schedule those assets for the best money based on risk. More than 15 years ago, actually, we did holistic risk management. So not just financial, but environmental, commercial, safety, engineering risk. All of those have a value to them that you can then balance that basis, and you need digital tools to do that. Then 10 years ago, we did advanced condition monitoring, so pattern recognition or whole plant monitoring. Again, there wasn't a solution on the market at that time, so we ended up building our own tool set. 5 years ago, we did maintenance optimization. So with the change in operation, you have to change your maintenance as well. Otherwise, you'll end up spending more money and taking more risk than you need to. And then 2 years ago, with the changing and ever-changing market conditions, we brought that into a single platform and added some mixed reality, which I'll show in a case study. So in all these cases, we've had to build our own solutions. So this is our own IPR, and we've always tested everything we've done on our own assets against solving a specific problem. So that's our history, and this is some of the headline benefits that we've achieved. So for the Ratcliffe power plant that I just spoke about, we have got about a 15 to 30% fuel saving. This one in the middle, it's a light oil fuel asset, so around $25,000 a startup, which if you're doing 20s to hundreds of starts per annum, that's worth a hell of a lot of money. Then these 15 to 10% expenditure and capex reduction, they're from changes in maintenance, so extending outage periodicity safely, changing the strategies to cut certain components on condition, not on time, or bringing the equivalent operating hours concept of gas turbines into pressure systems, etc. That given us big savings. And Uniper, we spend close to €1 billion on capex per annum, so it gives you an idea of the savings there. And then this 6-month payback was the payback for advanced condition monitoring on our gas fleet. And then the final one is efficiency gains. So generally we see anything between 0.1% efficiency improvement, or the best we've had is 2.6, but honestly speaking, that was a fairly dirty lignite asset that needed some fairly serious work. So it was a big number, but not the best asset condition to begin with. So those are some of the savings, but now I'm going to go into some case studies to make that realer. The first one is on virtual engineer and the safety challenges around that. So in Europe, we have a declining engineering technical knowledge base. Our engineers, or engineers that train in university, are being lost to the tech industry, the finance industry. So there's less people joining our industries. I'm pretty sure that we're all familiar with that across the whole of the world. There's a growing cost consciousness in the industry. So with the decline and the change in operation, the cost conscious nature has increased. And also travel is in fact one of the riskiest things we now do as a business. So we do as a business, maybe in the UK, for UK stuff, around 2 million miles per annum, which translates to, if you look at the road statistics, 2 fatalities on the roads driving. But that, thankfully, we've had no fatalities on the roads in the last 10 years. So it gives you an idea of that now being one of our most risky things and how we manage it. And last fatality in the UK was in 2006. So travel becomes one of the most risky things we do, and actually this virtual engineering piece can help reduce that. So our solution is to come up with some wearable tech. Here you see a Microsoft HoloLens on PPE equipment, and this person is actually doing some work in Amman in the Middle East. However, when you put this on, you create a new problem, and that is, how do we deliver this safely? So we've solved the problem of getting access to experts, but delivering this safely, where you've got a reduced field of view. You can see here, this is a reduced field of view, and all the other PPE equipment around it. How do we achieve that? So we've had to update all of our RAMs, so our risk and method statements. We've had to bring in additional sensors and equipment to advise, and that has allowed us to then perform some inspections. So here is the continued inspection in the Middle East on this was on a gas turbine, standard statutory inspection, and it meant that they got access to expertise which is not available in the Middle East, and we didn't have to send somebody traveling over, saving them money and reducing our risk profile. Then the next case study is on empowering the operator. with actionable information, and we do that through our thermodynamic solution, which is called ProATIS, which can assess the overall plant performance, individual components, which then helps you maximize efficiency and generation. We then take that into an online model where you can then see actual performance, so what's it doing with regards to fouling effects and other aspects as today. Then there's a standard performance, so what was it supposed to do by design, and then the delta between those effectively becomes your target performance. Additionally, we can then see for each of these individual parts of the plant, what is the impact of each of those components on its performance, which then enables us to do what if calculations. So what if I replace the condenser or clean the condenser, what would the impact be? What if I added a cooling tower or removed a cooling tower from operation? What would be the improvement? And we can do that because of two technical strengths in the thermodynamic software. So when we started building this 30 years ago, there was thermodynamic solutions out there, but they didn't handle heat exchange very well, and most of the equations were dealt in a linear manner. So if you want to ask it a different thermodynamic question, you had to rebuild the model. So ProATIS works with residuals, so instead of A equals B plus C, it's 0 equals A minus B minus C. And then we run effectively an optimization that then regresses on the mean, so you can handle the cyclical heat nature or the radiant heat aspects within the boiler. So as a result, the results are more accurate, particularly for complex large coal-fired boilers. Here is a case study of cooling towers. So we had a hypothesis that this asset, if we reduced or increased the number of cooling towers in operation, we could improve the efficiency. So the white line here is the number of cooling towers, so it goes from 14 to 13. This is what the system is predicting. If I took out one cooling tower, the green-blue line, in this case, the efficiency and generation would improve. And the bottom line is the pink-yellow one, that's saying what would happen to the efficiency and output if I added a cooling tower. All of this is normalized for operating condition and ambient conditions, and the target is to get it on this black line here. And it's for a 24-hour period. So you can see that in the morning, the operator should be taking out a cooling tower in its operation. And if they took that out, they would gain 0.05%. So in this unit, it's around 4 megawatts, which is a tradable capacity in that market. So they could be then getting that as either flexible payments or wholesale value. And to prove that it works, you can see here we took a cooling tower out, dropping it down to 1 minus, and then you can see here the system saying bring back a cooling tower back in because it will improve your efficiency, and that's what happened, and it's returned to good operation. This is in the control room of the site now, and then they take effectively action on the number of cooling towers each morning, afternoon, day, based on the weather conditions. The second case study is on the air inlet. So this is on GT. You can see here on 12 months of data, we've detected a drop in performance. Where at this point we don't know why. Then 6 weeks later, we picked up, because the unit had advanced condition monitoring, a change in differential pressure. So those two things together tell us that that is a blocked filter, or beginnings of a blocked filter. But importantly, we could say how much is being lost. So it was okay for the unit to take another couple of weeks, losing 0.5 megawatt, rather than take an unplanned outage and lose out on the revenue and the fines from the regulator. So it gives them financial prioritized information. The next case study is moving away from performance more into a reliability, availability space. And what we do is to try have the operators, maintenance teams back. So we've got your back so you can safely operate. And we do that through advanced condition monitoring, where we build, taking 10 to 20% of the signals of the asset, build around 150 models or digital twins. And we do that by, in this case, this example, I've got 2 dimensions, load and temperature. I can add a 3rd dimension that becomes pressure, and that then is a sphere of what is considered good operation. I can run this to unlimited dimensions. Our largest models are 117 dimensions for a complex cooling water system, and then we map that across all operating modes. Put some alarming ranges in place, and then during live operation, if it moves outside one of those planned spheres, then that indicates a potential fault. And that's really useful because power plants produce lots of data, and no engineer can look at every piece of data every 10 minutes. So here's some case studies of that in place. So this is a transformer that had a safety cordon around it. So the regulator identified a design fault that effectively meant we must put a safety cordon around it, and that meant the routine maintenance stopped. However, we detected an increase in winding temperatures outside what we considered good operations. So the actuals had moved outside the sphere, and then we've implemented, or we spoke to the site, said to them, look, we know about the environmental and the regulatory permit, but you're actually getting an increase in winding temperatures, so you should perform your routine maintenance, meeting the risk assessment. So the permit was raised, the risk assessment was completed, and the site went and cleaned debris, leaves, mud, waste off the top of the transformer, and then that dropped the temperatures back down to what was expected. So the worst case here is we avoided a trip on the asset, which would have probably cost them a couple of 100,000 euros in revenues, and potential loss of EOH on some components. And the best is, the worst is that we've saved on insulation life time. Here's another example where we don't just try to tell clients to come off if there's a problem. We try to enable them to safely operate. So those of you are familiar with vibration, we identified a potential rotor crack, and as some of you know, they're super rare in the industry and can be pretty catastrophic if they do happen or are unable to fail. Around May time, we identified a potential rotor crack. There's no way of knowing if this is the case because you've got to open up the turbine and you've got to cut the rotor in 2 to see, and at that point it's pretty much useless. So they had a planned outage at the beginning of July, and based on our vibration data and the temperature data, we enabled them to continue to run safely for another month. And you can see here the levels starting to creep up, all within the ISO guidelines, and we had heightened monitoring to enable them to do that in a safe manner. Then that was opened up just before the beginning of July. The scale ends on the 3rd, so 1st of July or last day of June. And when they did the RCA and they cut through the rotor, there was in fact a crack in the rotor. So we've enabled them to continue safely operate, get the revenue from the market, and avoid a catastrophic failure. And that's really quite important in the days of flexible operation where you need to ensure you're available when the money is there. The final case study I've got is on postponing an outage in COVID-19. So in this example here, we've got some tight clearances on the steam turbine, and they plan to expand those clearances in April 2020, but that wasn't possible. Now, the operators are not vibration experts, and these rubs that happened were well below and within the DCS alarm limits. However, when the trip happens, it comes really, really quickly in the space of minutes, often when the operator is not ready. And a trip in this market is particularly heavily penalised. So we created auto alerts based on the data which was sent to the control room for the team to act way before this acceleration of a problem happens. And it's saying here the alert's fired, so because they're running at reduced load, consider increasing your load to just manage the current situation and then bring it back down to the reduced load. And that's really important in this market because the unit's running at minimum load because that's where the money is. And if they're to come off, the fines for basically increasing instability of the grid are extremely high, whereas the fines for overgeneration are very small in this case. So in terms of a risk-benefit analysis, this was a safe thing to do and enabled the asset to continue to make money until mid-May, when we then completed the outage. So if we take all those things together, it's possible to alter your maintenance, and we alter our maintenance by effectively performing a strategy review. So a maintenance strategy review says, well, if I've got certain sensors in place, I've got redundancy, it's not a critical component, I could potentially run on a condition-based strategy. And we have 3 questions that we ask for every component that informs you: is it a condition-based strategy, a time-based strategy, or a run to failure strategy? And it's important that you use all 3 of those strategies. There isn't a one size fits all for every component. You need to use all 3 of them. So we do that review, we bring in commercial data, so what its expected future running is, and the historic actual data. And then that produces cash flows, planned outages, etc. So we did this in Uniper. We then effectively optimized our outages, so we moved them into the future. So far, in the case of some of our assets, that we removed a major outage from its complete lifetime, which saved significant sums of money. But most importantly, it brought a number of these assets back to being cash positive, saving us around 16% in capex, and as I said, making the cash flow better. So those are some case studies. Might be worth me just then saying you, how is this possible? It's possible because of the combined nature of engineering plus digital. No digital solution does everything you need yet. It's not like the retail sector where it's all right to be 80% accurate for clustering of customers, because you're going to make 80% more money with them. In a power station, 80% accuracy is just not good enough. So that's a really important facet of why we do this combined software plus service aspect alongside running on our own assets and being independent from equipment manufacturers. The other side is your 24/7 access and utilization of big data or machine learning technologies. So using the new technologies to enable some of the speed of processing and insight, and then combining all those solutions together as one piece to inform decision making. However, if you try to do all those digital solutions I came up with to begin with, you'll spend a lot of money and probably not get the complete payback. So you have to understand, is your asset in a base loading regime, or is it moving to a flexible regime where you switch from availability to availability in the money? And you're changing your operation from changing megawatt hours to chasing megawatt hours to chasing the volatility, i.e. where the money is. And depending on that, different solutions will get you more value. So in a base load environment, thermodynamics, absolutely, efficiency is going to gain you lots of money, but in a flexible one, it's a lot less valuable. Vibration remains roughly the same value because it's your main shaft line and you're effectively protecting or insuring against that. Risk management in a flexible operation becomes more important because you're operating the asset differently, so you're changing your risk profile. Advanced condition monitoring becomes more important because you're lengthening outage periodicities and you're running the asset in different ways than it previously was designed. So having the early warning is really important. And then broader performance monitoring is more important because of improving your startup. So it's not then just about the efficiency, it's about the cost of oil, it's about the cost of your consumables, the impact on the environment. So the performance monitoring becomes stronger there. And then your maintenance optimization becomes more valuable because in a base loading regime, you know, every 4 years you're going to do your major statutory outage. But in a flexible operating regime, that could be you end up doing a major one every 3 because you do lots of starts and stops, or it's every 6 because your operation is different. So in summary, that's what we've managed to achieve and our clients have managed to achieve. And I hope through some of the case studies and some of the advice on picking off areas that will get you value first, rather than trying to go after everything, is something that you'll find valuable. Thank you for your time, everyone.
Thanks, Peter. There is a question from one of the audience. The question is, can we please delve a bit? How do you strike a balance between cost and carbon competitiveness? Is there any work going on carbon capture in power sector?
There was 2 questions there I picked up. So yeah, that balance between cost and competitive
and carbon competitiveness.
Yeah, so it's really important to identify how your asset is expected to run and then pick the solutions that target your problem. So if you're starting to operate flexibly, then you're going to be interested in your maintenance costs and reliability. Whereas if you're base loading, you're interested in availability and reliability. So understand how your asset's going to operate and then use an asset management framework to select the key criteria, and then you won't invest in everything. Then with regards to carbon capture, that's something that Uniper is investing in, but it's not just carbon capture. There's lots of other waste from power plants, so heat, ash, etc. All of those have an environmental impact, and all of those can be made of use and made money from. So look at the complete output of a power plant, not just the carbon.
Take over. Okay, thanks, Peter. I've been a great presentation. You covered a lot of examples. I think I'm very sure that the audience will be quite benefited, and I hope that you will continue the cooperation with the Indian and global teams. Thank you. So we'll let you go now. Thank you.
You're welcome. And anyone wants to ask any questions, just find me on LinkedIn.
Yeah, we'll forward it to you.